Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all in today's session. Well, to access the notebook for today's session, you can access course page on my personal website arifpart.me. The other way is to download all the notebook files from course GitHub account arifpucit, and all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture number 6.27 of the 6th module Machine Learning for the course titled Tools and Techniques for Data Science. The title of today's session is Naive-Based Classifiers using Scikit-Learn. My dear students, this is the third session on Bayesian learning. In our first session, that is lecture number 6.25, I gave you a precise but comprehensive recap of all the basic probability concepts that are must to know in order to understand naive-based classifier. We discussed in detail marginal, joint and conditional probability with lots of examples using paper pencil as well as using Python code. In the second section, that is lecture number 6.26, we started with the proof and examples of Bayes theorem, and later covered all the nitty-gritties of a naive-based classifier. And I think we did 4 examples having discrete input feature and 2 examples having continuous input features. And we did all this using a paper pencil and the calculator, understanding all the math without taking any help of the Scikit-Learn library. My dear students, in today's session, I will start with a quick recap of the naive-based classifier, and then I will give you an overview of the 5 classes of the Scikit-Learn's family of naive-based classifier, that is Gaussian, Bernoulli, multinomial, complement and categorical naive-based. I will then do 2 comprehensive examples of using Sklearn's Gaussian and multinomial naive-based classifier. At the end, we will have some tasks that you need to do after listening to all this lecture and practicing it. So let's start playing. My dear students, let me start with a quick recap of Bayes theorem and naive-based classifier. Well, Bayes theorem was actually introduced by Thomas Bayes, which is a way of calculating conditional probability without using the joint probability. Well, in our last session, we derived the formula of Bayes theorem, which is shown in green color over here. The probability of the output label y equals k given the input features x. This is the posterior probability, and which is equal to the probability of y equals k, that is the prior probability, times the probability of x given y equals k, which is the reverse of posterior probability, also called the likelihood, divided by the probability of x, which is called the evidence or normalization constant, and this must be non-zero. Well, in our previous session, we moved step by step and have understood as to how we arrived to this naive-based classifier formula shown in magenta color over here, and this we derived from the Bayes theorem formula, and this is called the MAP or maximum a posteriori decision rule. And this formula shown in magenta color, it is called MAP rule because it chooses the value of this output label y that maximizes the posterior probability. And this formula in magenta color says that the predicted value of y, that is y hat, is equal to the probability of y equals k times the product of all the probabilities, rather the product of all the conditional probabilities of input features x sub I given y equals k. And this argmax will return the value of the output label y that has the maximum probability which will be assigned to this y hat. Well, my dear students, unlike deterministic classifiers like KNN, decision trees and support vector machines, this naive-based is a probabilistic classifier as it outputs the probability estimates for the k classes. And the naiveness of this classifier is because this algorithm makes an assumption that all the input features, that is this x1, x2, so on to xm or n, are independent to each other and make equal contribution to the output label, which is mostly not true in reality. Although naive, but this classifier performs very well in applications like sentiment analysis, classification of spam emails, recommendation systems, article categorization, search engines, and so on. And furthermore, as compared to other machine learning algorithms, naive Bayes is fast and therefore is good in making predictions in real time. Well, my dear students, we have explored the math behind the naive Bayes classifier in our previous session by doing a lot of examples using paper, pencil, and calculator. And today we will see as how the Scikit-learn library makes a developer's life easy by hiding all the details behind its API. Well, the naive Bayes module of Scikit-learn comes bundled with the 5 estimator classes: Gaussian, Bernoulli, Multinomial, Complement, and Categorical naive Bayes. Now a $100 question is when to use which of these naive Bayes models for the classification task. Well, we use the Gaussian naive Bayes when the input features are continuous values. For example, as shown in this left table, height and weight, they are continuous values that can be used to classify the gender of a person, being male or female. Moreover, a Gaussian naive Bayes model assumes that the feature values, that is these columns, follow a Gaussian or normal distribution. The next is Bernoulli naive Bayes and is used when the input features are Boolean and are expected to follow Bernoulli distribution. For example, if you consider this middle table over here, where each observation is an email, the text of an email, for example, and the output label is either ham or spam. Note the values are Boolean. For example, one under the lecture column in the first row over here specifies that the word lecture exists in the first email. Similarly, a 0 under the lecture column in the second row over here specifies that the word lecture do not exist in the second email. I hope this makes sense. Well, the next type of naive Bayes classifier is a multinomial, which is used when the input features have a discrete count. For example, if you now consider this right table, which is the same text classification dataset as shown in green over here, but over here instead of keeping a 0 or 1 for the non-occurrence or occurrence of a word respectively, we specify the count. That is how often a word occurs in a document. Well, my dear students, other than these three, this complement naive Bayes is an extension of multinomial, which is more suitable for imbalanced datasets and often outperforms multinomial naive Bayes on text classification tasks. And this finally, this categorical naive Bayes is useful if the features are categorically distributed. And for this, we normally encode the categorical variables in numeric format using the ordinal encoder. And last but not the least, all these classifiers work fine with the output labels being binary, multinomial, ordinal, or multi-class. Excuse me. Well, my dear students, now you have a fair idea about the Scikit-learn's family of naive Bayes classifiers. Let's move ahead and do a few examples. Okay, let me load the breast cancer dataset. You can load it from the UCI machine learning repository. You can download it from there, or you can use the load_breast_cancer method of the datasets module of Sklearn as well. Let me just check out the shape. Okay, So this dataset has 569 observations with 30 numeric attributes, which are computed from a digitized image of FNA of a breast mass. Well, the output column over here at the very end is target, specifying a 0 or 1. I think a 1 for benign, that is no cancer, and a 0 for malignant, showing the presence of cancer. Let me check out the value counts under the target column. Let me say df target dot value counts. Okay, so there are 357 benign examples represented by 1, and 212 are malignant. Well, my dear students, we need to train and later evaluate the Scikit-learn's Gaussian knife-based model on this dataset. However, I will go step by step, and first we will do a bit of exploratory data analysis, which we have been doing in our previous sessions. And you all know that EDA has a no set methodology. However, here is a short checklist that one can follow. Let me just call the info method on the data frame to check the data types and null values, if any. So all the columns are of numeric data type having no missing value. Let me call the describe method as well, df.describe. So this displays the mean, max, mean, standard deviation, and the 3 quartiles or percentiles. Let us check out the distribution of one of these columns. Say this mean radius. We can use the Seaborn library for this, sns.hisplot. Let me say data equals df, and let me say x equals to this value. So we have SNS not defined. Let me say import Seaborn as SNS, and let me run again. Sorry for the typo. SEA. Okay, sorry for this. Well, this seems to be normally distributed, although a bit skewed on the right, having some outliers as well over here. And let me use the box plot, Seaborn's box plot method, to check the outliers under this same column. Let me say sns dot box plot. Let me say data equals df, and let me say x equals to the same value. Okay. So you can see outliers on the right, of course, over here. And on the same pattern, my dear students, I strongly recommend that you should do the exploratory data analysis of this data set. Time spent on EDA never goes wasted. Let me move ahead and talk about the next phase, that is the data pre-processing phase. Well, data pre-processing are actually the actions that we need to perform on the data set in order to make it ready to be fed to the machine learning model. And my dear students, I have made separate video sessions on each of these 6 pre-processing feature engineering tasks. And in today's session, let me give you a quick recap of all these very quickly. And the first is missing value imputation. If you want to do univariate imputation, you can use either Panda's fill-NA method or Sklearn's simple imputer transformer. And on the other hand, if you want to do multivariate imputation, you can use Sklearn's iterative or this KNN imputer. And I think I have covered these in detail in lecture number 6.8. And as far as missing values are concerned, you need to remember that knife base is one of the models that can handle missing data at its own end. So you need not to do the missing value imputation in case of the knife-based classifier. And before feeding the data to the machine learning model, we need to encode. We of course need to encode the data to numeric values, and to encode the nominal data, we we use one hot encoder, and we all know that the nominal data is the data having no intrinsic order like gender and city. In case to encode the ordinal data like passenger class, shirt size, we use ordinal encoder. And finally, to encode the output label, we use Scikit learns label encoder, and all these are transformers. And for details on this topic, you can watch lecture number 6.9. Okay, my dear students, if you want your model to perform well, especially when your dataset contains columns having different units, you must perform feature scaling on all the numeric columns. And the most commonly used technique is a standard scalar transformer, which performs a standardization of data. That is, rescale the data so its mean becomes 0 with a standard deviation of 1. We should use standard scalar when the data under the column is normally distributed. On the other hand, if the data is not normally distributed, one should use a min-max scalar or a robust scalar, which will rescale the values within a new range of 0 and 1. And since naive-based classifier is not dependent on the distance, so feature scaling is also not required as such. However, feature scaling is a must to do for distance-based algorithm like linear and logistic regression, KNN and support vector machines. Okay. My dear students, the next pre-processing task is detecting and handling outliers. To detect the outliers, you can use the z-score method if the data is normally distributed. That is, any value below mu minus 3 sigma or above mu plus 3 sigma can be considered as outlier. On the contrary, if the data under a column is skewed, we should use IQR method, interquartile range method. Any value below Q1 minus 1.5 times IQR and any value above Q3 plus 1.5 times IQR can be considered as outlier. And for multivariate, one can use a scatter chart and depth or density based methods to detect outliers. And once detected, you can use this trimming, capping and discretization techniques to handle the outliers. My dear students, this naive Bayes is highly impacted by outliers because the naive Bayes classifier assigns 0 probability for all the data instances that it has not seen in the training set, which of course creates an issue during the prediction time. Okay, I think enough of recap on data pre-processing as far as this breast cancer dataset is concerned. We do not need to do much of the pre-processing. As you can see, all the columns are numeric and we do not have missing values. So let's do a train test split and fit the Gaussian naive Bayes model. Well, this code cell separates out the 30 input features, and in this X variable, this df contains 30 input features and one target column. And over here I am just getting the 30 input features in the X column and the output target in Y. It then uses the famous train test split method with a test size of 20%, which returns a 4-valued tuple. Let me just execute it. We have used this method many a times. Note that out of a total of 569 observations, 455 are kept in the training set and 114 are kept in the test set. So we have our X train, X test, Y train and Y test. Okay, now let's create an instance of the Gaussian naive Bayes model. I have to import the Gaussian NB model from Sklearn's naive Bayes module. Let me just execute. I have the model instance now. Next, we need to train the model using this fit method and passing it the X train and Y train. Now we have the trained instance of the Gaussian naive Bayes model, which has calculated, of course, the sample mean and standard deviation of all the input columns for both the cancer and the healthy groups. The model has calculated the PDF, or that is the probability density function values for all the input features using this Gaussian formula. And my dear friends, remember that knife base is not a lazy classifier, rather is an example of an eager or generative classifier. And this is because it learns a probabilistic model based on the training data during the training phase. And this model is then used to make the predictions on new unseen instances without requiring the original training data at the prediction time. So that is why it is not lazy. This is one of the interview questions that people normally ask once you go for your graduate studies or maybe in the industry as well. Okay, so we have the trained instance of the Gaussian knife-based model. Now it's time to carry out the predictions. And remember, we have 114 observations in the X-test dataset for this purpose. Let me first call the predict_proba method on the trained model by passing it X-test, which will return the two posterior probabilities. That is the probability of y equals 0 and y equals 1 given all the input features. And since this is a binary classification problem, so it is returning two probability values for each data set, for each data point rather. And since there are 114 data points, so we will get 114 values. My dear friends, I hope this is making sense. These are the two probability values for probability for y equals 0 and probability for y equals 1 given all the input features for the first data point and for the second data point and so on to 114 data points. Excuse me. And over here, my dear friends, I am calling the predict method now instead of calling the predict_proba method, which use this argmax function, which will return the value of the output label y that has the maximum probability. And this is what is called the maximum a posteriori or map decision rule. Let me just execute it. I hope this is making sense. You see the first value is 0 and this is greater than this value. You can map these two outputs. Let me check this out with the ground labels as well. This ypred contains the predicted y values for x test and the ground label is there in y test. Once again, you can compare these 114 predicted values, these 114 predicted values and these 114 actual ground truth values. And you can construct a confusion matrix calculating different for the calculation of different metrics for evaluating your trained model. So instead of doing this manually, you can of course do that using the confusion matrix method. Okay, so this takes us to the final step, that is the model evaluation, which is the process of using different evaluation metrics to understand a machine learning model's performance as well as its strengths and weaknesses. And for classification algorithms, we have discussed in detail the commonly used metrics like accuracy, precision, recall, F1 score, AUC, ROC curve. I think I have covered this in lecture number 6.22 for the first time. Anyways, well, my dear students, we all know that this confusion matrix is a scale matrix, n by n scale matrix, that is used to define the performance of classification algorithms. And this is called confusion matrix because it shows the statistics where a trained classification model gets confused. Let me just execute this code. Okay, great. So we have our confusion matrix over here. My dear students, if I consider 0 as healthy and 1 as cancer patient, then this 37 is true negative and this 65 is true positive. This value 8 in the top right cell is false positive or type 1 error, which means that there are 8 healthy persons who are predicted as cancer patient by our model. And this 4 in the bottom left cell is false negative or type 2 error, which means that there are 4 patients who are wrongly predicted as healthy by our model. Remember, for this use case, type 2 errors are more dangerous, where a cancer patient is classified by the model as healthy. Okay, how the code is clear. We have seen this many a time. My dear students, finally this code cell over here, this use Sklearn's matrix module to compute and display the accuracy, precision, recall, F1 score, as well as a comprehensive classification report. Let me just execute. So accuracy comes out to be 0.894, which means 89.4% of the times our model predicted correctly. The formula to compute accuracy score shown over here is the sum of the true positives and true negatives divided by the count of all questions asked from the classifier, that is TP plus TN plus FP plus FM. Remember, for highly imbalanced datasets, accuracy does not prove to be a good evaluation metric. So we move on to the next metric, that is precision, which evaluates the model based on false positives or type 1 errors. As you can see in its formula over here at the top, which is the TP divided by TP plus FP, and this comes out to be 0.89. On the contrary, my dear students, recall evaluates the model based on false negatives or type 2 errors, and you can see this in this formula over here at the top again, which is TP divided by TP plus FN, and this comes out to be 0.94. For this breast cancer dataset, of course, we will prefer reducing type 2 errors, that is a higher recall score, as we do not want a cancer patient to be classified as healthy. Anyway, finally we have this F1 score, which is the harmonic mean of precision and recall, with its formula mentioned over here, having output value of 0.915. And remember, F1 score will be high only if both precision and recall are high, and low if any of precision and recall are low. And do note that this F1 score, that is 0.91, is a bit tilted or inclined towards the precision score, which is this 0.89, which is lower than recall. So this is because of the harmonic mean. And my dear students, finally I have shown the classification report. I've used this classification underscore report method, and I've passed this y-test and y-pred, and this has given us this classification report. Okay. Note that this classification report displays the precision, recall and F1 score for both class 0 as well as for class 1. The above methods of precision, recall and F1 scores over here, they by default considered class 1 as positive class, and you can compare their values do match, 0.89, and over here we have 0.89, and the recall score is 0.94, and we have 0.94 over here. And this support column specifies the number of samples of both classes on which the metrics, these metrics are computed. That is 45 instances are used to compute these metrics for class 0. That is, there are 45 instances that belong to class 0 and 69 metrics for class 1, and this 45 and 69, they sums up to 114, which is the count of the data in our testing data set. I hope this makes sense. And finally we have macro average, precision, recall and F1 scores, and these are the average of the scores of both the classes, and is used when you want to give equal weight to both classes. And this weighted average, precision, recall and F1 score are the weighted average of the scores for both classes, where we multiply the class metric with actual instances of the class. And this we use when we want to give more weight to a class having more number of samples. I hope this makes sense. So that is it for the example 1, I think. Yes. We are done with implementing the Gaussian knife-based model on the breast cancer dataset having numeric features. Now let's do another example and use multinomial knife base on the textual data, which falls under the domain of natural language processing. And my dear students, this NLP actually enables computers to understand and respond to human languages in written, verbal as well as in sign form. Let me just load this toy dataset from this CSV file. Excuse me. And it contains 18 sentences or documents, each labeled as positive or negative. And given this toy dataset, the objective is to train a multinomial knife-based model and later do a prediction of new sentences. And before I proceed any further, remember in this session I will try to keep things simple and will give you an abstract level description of the concepts related to NLP. As our main objective over here is to apply multinomial knife-based classifier on this toy dataset. Well-interested students can watch my playlist on natural language processing, whose link is shown over here. Okay, so let's just check out the shape of this dataset as usual. Okay, so this is data. Let me say data.shape. So you can see that we have 18 sentences and we just have 2 columns. Let me call it info. Great. So there are no missing values and both columns are of object type. Let me do the easy task first, that is encode this output column, that is label, by assigning a let's say 1 to the positive class and a 0 to the negative class. Let's do that. You can do it either by calling this map method on the output column label of this data frame and passing it a simple dictionary that maps the string positive to a value of 1 and negative to a value of 0, and this will create a new column in our data frame. Let me just execute. I hope this makes sense. Well, if you do not want to use the map method, you can use the Scikit-learn's label encoder transformer, which will sort the values of the output column alphabetically and then assign each category value a unique integer starting from 0 and so on to n-1. And this code shall actually first import the label encoder class from pre-processing module of Sklearn. It then create its instance and then call fit_transform method by passing it the last column, that is the column to be encoded. It returns a series object which is further saved as a new column in the data frame. Let me just execute it. So here it is. You can note that both the numeric columns, they do match, and over here in these 2 code cells I have just assigned the document column of the data frame containing text sentences to X and the numeric label to a variable Y, and this contains 1 for the positive class and 0 for the negative class, and of course X and Y are series object. My dear friends, before we transform this textual data of sentences to numeric data, we have to pre-process it. Okay. Well, the way we have been pre-processing the numeric data in case of our previous example, or as we did many a times in our previous sessions, My dear friends, we need to pre-process the textual data as well. And this pre-processing can be divided into three parts: text cleaning, basic pre-processing, and advanced pre-processing. Well, in the text cleaning part, we normally perform tasks like a removal of unnecessary digits, spaces, new line characters, HTML tags, URLs, and punctuations. In the basic text pre-processing, the tasks we perform are case folding, expanding contractions, handling chat words and emojis, spelling corrections, tokenizations, n-grams, and stop word removal. In advanced text pre-processing, we do stemming, lemmatization, part of speech tagging, parsing, and maybe co-reference resolution. My dear students, I have covered all these text pre-processing tasks in two video sessions of natural language processing module, whose links are shown over here. Well, the dataset on which we are working in today's session is quite simple and it is quite clean. Therefore, I think it will give reasonably good results even if we do not do all this pre-processing on this textual data. And doing all these tasks is beyond the scope of today's session, so let me move ahead. Well, my dear friends, once the text pre-processing is done, we need to transform it into their features to be used for modeling. In simple words, we need to assign numeric values to the words within our document in such a way that the number represent the meaning of that word. The process of converting text data into vectors of real numbers is normally called text vectorization. And these are the various approaches of converting text into vectors, which are broadly classified into two categories. The first category use a frequency or statistical based approach. Label encoding and one-hot encoding fall into this category. But for textual data, we normally use and prefer bag of words and TF-IDF techniques. The second category says that don't count but predict. This category is also known as word embeddings, which maps a single word into a vector of a real number of maybe 300 to 400 dimensions. We can of course design and build our own models using deep learning techniques, but mostly we use existing pre-trained models like this word2vec by Google and this fast text by Facebook. And in today's session, I will use the simplest technique, that is bag of words. Interested student can watch my YouTube lecture on feature engineering, text vectorization. You can click this link to go to that YouTube video. Let me move ahead and talk about bag of word encoding. Excuse me. Well, my dear friends, bag of words encoding is the most commonly used text vectorization technique. And before we use Sklearn's count vectorizer transformer for this task, let me give you a quick conceptual understanding of this encoding technique. Consider these three documents consisting of 5, 10 and 5 words respectively, shown in magenta color over here. The first sentence or document has 5 words, the second has 10, and the third has again 5 words. We need to build a vocabulary of this corpus, and a corpus is nothing more than a collection of documents. This vocabulary is actually a collection of all the unique words, and we also need to assign a unique number to each word. For this, we alphabetically sort all the words and then assign them numbers starting from 0, as shown in this dictionary in green color. The word also is assigned a number 0, amazing is assigned a number 1, and so on to this YouTube is assigned a number 9. So that means this corpus of 3 documents or sentences has a total of 10 unique words, which forms its vocabulary. These two tables are known as document term metrics that describes the frequency of terms that occur in a collection of documents. each row corresponds to a document in the corpus, which is just a collection of document. Each column represents a unique word in the vocabulary. For easy understanding, I have mentioned the words as column labels in upper table, but in reality the labels are a numeric column as shown in the lower table. And finally, the values inside each cell are actually integer values which represent the frequency or count of that particular word in that document. And if a vocabulary word do not appear in a document, you can see a 0 in that cell. Well, my dear students, the main advantage of bag of word over label encoding or one-hot encoding is that using bag of word we encode every document as a fixed size vector, irrespective of the number of words in that document. And in this case, the size of the vector is 10. And these vectors are shown in blue color over here. You can see this document 1 having 5 words is encoded as a vector of size 10. This document 2 is also encoded as a vector of size 10, and this document 3 is also encoded as a document of size 10. Now these vectors can be fed to a machine learning algorithm like naive Bayes for training and prediction. Okay, so let us create a document term matrix of our toy dataset. So this is the toy dataset, 18 sentences or documents that are there in X. My dear students, to programmatically create a document term matrix or bag of word representation of this dataset, we need to perform 3 steps. First of all, we need to tokenize all the sentences or all the documents. Then we need to create a vocabulary of unique words sorted in alphabetical order. And finally, we need to populate the cells of the document term matrix with integer values representing the frequency of words of the vocabulary in a particular document. And this we have seen above. But to a good luck, Scikit-learn comes with a count vectorizer transformer that will transform this corpus of 18 documents to a sparse matrix having 18 rows, and the number of columns will of course be equal to the vocabulary count. So this count cell first import the count vectorizer class of Scikit-learn. It then creates an instance of the count vectorizer object with default attributes and save it in a variable named CV. Let's execute. So you see its type is count vectorizer. Let me call now the fit underscore transform method of this transformer object by passing it X containing all our textual data. And this will learn the vocabulary and will return a sparse matrix which I am receiving in this variable BOW. Let's execute. So you see it has returned a 18 by 55 sparse matrix. This is the size of the matrix. 18 rows, 1 for each document, and 55 columns, 1 for each word in the vocabulary. So that means this dataset has 55 unique words, I think. Okay. Also note that instead of storing 990 values, 18 into 55, 990. Instead of storing 990 values being a sparse matrix, it has just stored 93 elements, that is just the non-zero elements. Well, we can of course call the numpy 2dense or 2array method to change this sparse matrix to its corresponding dense representation. Let me just execute it. So this is the matrix. This is the first vector having 55 values. This is the second vector representing the second sentence having 55 values, and of course we have a total of 18 vectors. Great. My dear students, do map the values of this first vector with this first sentence, that is Arif YouTube lectures are amazing. 1, 2, 3, 4, 5 words, and you can see 1, 2, 3, 4 and 5. There are 5 ones, rest all are 0. Anyways, for better visualization, my dear friends, let me convert this numpy 2D array to pandas data frame. Let me just execute it. Great. Over here the column names are numeric, but if you want to have names over here instead of these numbers, you can use this get underscore feature underscore names underscore out method of the count vectorizer and assign these values to the columns attribute of pandas data frame. Let me just execute. Now this makes more sense. Great. So this is what is known as document term matrix, where each row represents a document in the corpus. We have 18 rows, and each column represent a unique word in the vocabulary, and of course there are 55 unique words. And finally these cell values, these are the integer count of that word in that document. I hope this is making sense. Great. Okay, my dear friends, I think now we have our data ready to be fed to the machine learning model. So first let me do a train test split. This code cell will do the job. Do note that the first argument to the train test split method, this has to be the document term matrix, and this bag of word is actually a sparse matrix, so I'm calling the toArray method to convert it into a numpy 2D array. Let me just execute it. So you see, out of a total of 18 documents, 14 goes to the training set, and just 4 goes to the test set. Now let's create an instance of the multinomial knife based model and call the fit method on the model instance by passing it xtrain and ytrain. Let me execute. So now we have a trained instance of the model. Next step is to evaluate on the testing data. And let me first call the predict underscore proba method as usual by passing it xtest having 4 documents. Naturally we have just 4 documents in xtest. Let me call it. So these are the 4 posterior probabilities. This first column represents the probability of the sentence of belonging to class 0, while this second column represents the probability of sentences of belonging to class 1. So this first sentence belong to class 1 because this probability is greater. The second sentence belong to class 0, the third belongs to class 0, and the fourth belongs to class 1. Let me now call the predict method, which will use the maximum a posteriori or map decision rule and will return the value of y that maximizes the posterior probability. Let's just execute, and great. You can see the same result. You can map this output with these probabilities, and these are the ground realities. You can compare these y predicted values with the y test values. You can see one of the prediction is wrong while the rest of the 3 are correct, and we can create a confusion matrix from this. Let me just quickly show you the matrix. Great, same results. Finally over here, let me just check out the accuracy, precision, recall and F1 scores as well. Hope the output of these functions and the classification report is clear to you all. We have discussed this in detail while doing example 1 of Gaussian knife base. Please do map these values, particularly this macro average and weighted average. This will make more sense over here because you can see the different values as compared to what we have seen in example 1. Okay, fine. Well, my dear friends, let's now predict a new sentence that is not there in our toy dataset, not in the training, not in the testing part. and the sentence is, YouTube lectures are great source of learning. This seems to be a positive sentence. Let's see what our classifier classifies it to. But for this, we first need to transform this sentence to a numeric vector using our already trained count vectorizer transformer, that is CV. So I call the transform method on this CV and pass it this new document, and I will get a vector, a sparse vector. but I am converting it to array, so I have got the vector. So this is a vector, 55 values, and 1, 2, 3, 4, 5, 6, 7, and just 7 ones. Okay, now in order to predict, I just call the predict method, pass it this new vector, and it will return me either 0 or 1. So it has returned me 1. That means it has predicted that this sentence is positive. Great. And in the similar fashion, I can check out a negative sentence as well, and that is, I am sick and do not want to stay in this house. This seems to be a negative sentence, and for this, once again, I need to transform it, and then I need to call predict. Great. Great job done. So our model has classified this sentence as negative. Okay, my dear students, so here is the task for you to do. Let me load a real world dataset now from this SMS spam collection file, which is a simple tab separated file having a label along with text of SMS in a single line. You can also download this file from this UCI machine learning repository by clicking this link. Well, this dataset contains a corpus of 5,572 SMS messages labeled as ham or spam. My dear students, I will like you to build, train and evaluate a multinomial knife based model using what we have learned today. And if you do not get good results, try applying different pre-processing tasks as well to clean this data, and interested student can further try to improve the results by using the TF-IDF vectorization technique instead of using the simple bag of word. And I'm sure that this will be fun for you all. So that is it for today's session. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.